So we're finishing up the enthalpy part that isn't in Chemistry 30. We're working from the AP Advantage Chem 1 workbook. So this is Chapter 4 in EdgeVantage 1. Okay. So there's a lot of different types of energy. I just want to make sure you're all really familiar with those as we get into enthalpy again. So radiant energy we hadn't talked about really since Chemistry 20. Okay. Back in Chem 20, we could quantize based on wavelength what is the radiant energy, okay, or the electromagnetic radiation. Okay, so maybe think of that as energy from the sun. Kinetic energy, we use a lot energy of motion. Just want to emphasize in chemistry that energy of motion often isn't translational, but it's vibrational. Okay? As molecules get hotter, they vibrate. Okay? Thermal energy, okay, we're really getting into thermodynamics a little bit more, okay? The energy associated with the random motion, okay? It's not our definition of temperature, but the energy form of temperature. The more thermal energy something has, the hotter it is, okay? Chemical energy, energy stored in chemical bonds. And then we've got potential energy, energy due to its position, okay? Now, our chemical energy is really a form of potential energy, or so you can have energy stored based in the position of one atom to another atom. Okay? So I just want to make that connection. Heat, this is our Q that we were calculating in thermodynamics. Okay? So heat is energy that moves from one circumstance to another, particularly for us from the system to the surroundings. Thermochemical change is this move in heat that we've been studying. A few other terms I just want to recap. We've talked about system and surroundings. We're going to label them a lot more in this unit as we work our way into entropy and particularly Gibbs free energy. So the system, okay, we might have the enthalpy change of the system, and I'll go SYS, or maybe change in entropy of the system. I never wrote in system before. It was always just implied. And in thermodynamics, when no subscript is listed, it is the system that is being referred to. Okay. And then we got the surroundings, the rest of the universe. This is where our heat went before. We never labeled it, but that's where we did our Q calculation. Okay. As we get into entropy, disorder, chaos, we might be talking about the system, which is what is the disorder, the chaos of the chemicals, or we might be talking about the surroundings, and I'll use SURR as my subscript. Okay. That'd be the environment around the chemicals, okay. The air, the water, okay, the disorder, that the change in disorder there. Okay. Now we have three types of systems. You're probably familiar with these. Okay. When you design a system, or a reaction, you might have an open system. Okay. So an open system can exchange both mass and energy. Okay, we typically don't want this. Okay, we typically want to control a bit more than we would have in an open system. Okay. Particularly for a course like Chem 20 and you're doing stoichiometry, you're often happy with a closed system. You can exchange energy but not mass. Okay. You're doing stoichiometry. You want to predict how much product you'd get. You want to weigh how much product you'd get. Okay. You did that. Okay. You didn't have to worry about trapping that heat. If it was exothermic, the heat could just go out and you could lose it and it didn't matter. If it was endothermic, you could absorb some heat and it didn't matter. Okay. Now in thermodynamics, where we're measuring heat, we often need an isolated system, can exchange mass or energy. So I'm going to keep going a little bit more detailed into thermodynamics. The first thing to highlight, something we've been measuring all along, or a category of measurements, we've only been measuring what's called state functions so far, and that's all you can measure in thermodynamics. So a state function could apply to any of the sciences, okay, is a property, okay, maybe volume, that when it's changed only depends on the initial and the final conditions. Okay. So energy, okay, pressure, volume, temperature, they're all state functions. Okay. If you want to know the change in volume, all you need is the V final and the V initial. You don't care how you got there. So if you started at 50 milliliters and you ended up at 100, the change in volume is 50. Okay, it doesn't matter whether you overshot the 100 and then came back down. The pathway doesn't matter. Okay. Now, things that aren't state functions would be how far your car has driven. Okay. If you know the odometer reading of your car, but you don't know the path, okay, you wouldn't know. So take a step back. If you know where your car is today and you know where your car is tomorrow, okay, you don't know how many kilometers it's driven. Okay, you'd have to know the path that was taken. So if you know your car is in Calgary today and Lethbridge tomorrow, okay, you would know the distance between the two places, but you wouldn't know the displacement of the car. You wouldn't know how many miles are on it. Okay. So there are many things, we're not going to study them, that you have to know the pathway. It matters. You can't just do V initial and V final. We get really used to in chemistry and physics going something initial and something final. Change in temperature, again, is a state function. We can relate that to energy. We only need to know T initial and T final. Okay. So this is sort of already mentioned in thermodynamics, we can't study path-dependent quantities. Okay. We can only study initial and final dependent. Okay. We'll be looking at the first law for a minute, and in the next lesson we'll be looking at the second law of thermodynamics. First law, probably the simplest. Okay. Energy can be converted, but it can't be destroyed. The total sum of the energy in the universe is a fixed number from day one. And all that's happening in the universe is energy is changing its type. And in this course, we're going to eventually be getting into not just type, but how much useful energy is there, which is not a constant. The amount of useful energy in the universe is going down and down and down, and someday will run out. So there will be an end of the universe, sadly, at least according to thermodynamics. Okay. Okay. So measuring the total amount of energy, trying to work right from the first law of thermodynamics can be quite difficult or impossible. Even a simple lab setup, measuring the total energy in your chemicals will be pretty much impossible. The kinetic, the potential, the nuclear, okay? There's probably a list of 10 different types of energy that's in those chemicals, okay? What's often measured in thermodynamics is a quantity we haven't talked about called internal energy or enthalpy, okay? Or we'll get into entropy or we'll get into Gibbs. So we're going to start with internal energy. Okay. where internal energy, I'm using symbol U. Some university textbooks use U for internal energy. Other books will just use E. I'm avoiding the E because that's a little E is used for a lot of other types of energies. So internal energy U is just the potential plus kinetic. So the change in internal energy just internal energy final minus initial. It is a state function, so we can do this. So we have a journey. I'm trying to get somewhere. We're going to get there and then use it at the bottom of this slide. Okay. So the change in energy, or internal energy, ultimately has to sum to zero in a whole reaction between all the pieces. So if we look at the change in internal energy of our system, plus the change in internal energy of our surroundings. So maybe our system loses 100 kilojoules. Okay. Our surroundings must gain 100 kilojoules. Okay. The first law of thermodynamics says the two must sum to zero. So if we want to know the change in internal energy of our system, okay, that's just the negative of the surroundings. Okay. And this is kind of exactly what we do with enthalpy, or we did with enthalpy already. Okay. Okay. So this isn't a new thing. We want to know that, or we did want to know that in thermodynamics, but we couldn't measure it. So we measured the change in enthalpy of our surroundings. That was Q. Whatever Q did, we knew it came from the chemicals, and we just put in the right sign. So that's all that's going on here. Okay. Well, we're going to solve for the change in internal energy of the system by breaking apart the surroundings. There's two forms of energy that you're going to have from the surroundings. One that we already studied was that heat that came out. And that's all we studied in regular 30 was Q. Okay. We didn't factor in, because we weren't doing internal energy at the time, the work that was done by the chemical reaction. And we're going to look at those two pieces now. And that's the theme for this lesson. So the change in internal energy of the system is Q plus W. Okay. We often don't write system. We didn't in Chem 30. I'm going to take system out when there's no subscript. That's what's implied. So Q we already know about. MC delta T is how we get Q, so we're not going to do any examples there. We're going to talk about the work and what type of work do chemicals do. Okay. If you think of typical work, maybe physics in science 10, you might think of force times distance. If you push something a certain distance, that is work. Well, chemicals can do the same thing. We're going to measure it a little bit differently. But if the chemicals either create a gas or use one up, if a gas is created, that gas is going to push against the surroundings. Okay? That pressure, which there's force embedded in pressure, is going to be pushing against something for a certain distance. Okay? And that's how we're going to get our work in our chemical reactions. So work from a physics point of view, which is where we're going to start, okay, is at force times distance, okay, or for us as chemists, okay, we're going to look at PV work, pressure times volume work. It's actually minus P delta V takes care of the right sign for our work. So let's just talk about how on earth pressure times volume could be energy. So if we think of pressure, what is pressure? There's a force component, but it's per something. Pressure is force per unit of volume. Okay? And then I'm going to break volume down a little bit more. Volume is just 3 dimensions, length, width, height. Okay? So there's a lot of subscripts I could use, but I'm going to call some distance cubed. Okay? The length, the width, the height. Okay? And what is volume? Sorry, distance. Jumping ahead, force is pressure, not per volume that I said. I was jumping ahead. What is the right thing? What should have I said? It's force per, not, so force would be the pressure I put against a area. Okay? So it's not distance cubed like I first wrote. It's distance squared. It's an area. Okay? A flat surface, or it doesn't have to be flat. Okay? But it's a length times a width. Okay? Okay? The volume is the length, the width, the height. Okay? That's cubed. Okay? So if you simplify pressure times volume, we've got 2 distances, or distance squared, the volume distance cubed. So that's where the force times the distance of PV work comes from. Okay? So now I want to take care of the sign. We're good with the signs, hopefully with Q. We'll recap Q again. It's the same convention. Okay? When work is done by the system, okay, the system is our chemicals, that work is going to be negative. That's energy being lost as the system does work on the surroundings and transfers energy to the surroundings. This is when our change in volume is greater than 0. Something, this chemicals are creating a gas and it's expanding, pushing out against the environment, okay? Doing work to the environment, sending energy to the environment. And this formula will give you that negative. If delta V is positive, okay, and P is positive, then we got minus P delta V, and you're going to get that negative work. So the opposite, okay, if the work is positive, this is when the volume is shrinking. The surroundings are now doing work onto the chemicals, pushing on the chemicals, transferring energy to the chemicals or the system. We would have a negative delta V term and a negative in our formula. Those 2 negatives would cancel, which would give us our positive work. Now for Q, we've already done this. When heat is absorbed by a system, we'd call that endothermic. We'd call that positive heat going into the system. And most of our reactions are exothermic. When heat is released, heat is being lost by the system, and that's a negative. So it doesn't matter whether it's work or heat. When the system is doing something to the surroundings, it's either doing work on it or sending thermal energy to it, okay, the sign is going to be negative. And it's negative from the perspective of the system. Okay? That's our perspective with the plus and the minus. Okay? Anytime the surroundings is sending thermal energy to the system or it's doing work onto the system, the sign is going to be positive, whether it's Q or whether it's W. Okay? So it's a consistent trend. We're not learning something different here. We're just adding in the work part. Okay? So you could use the formula and the sign to make sure you keep things straight. I encourage you to think your way through it, okay? What is going on? Is the gas expanding, negative, or contracting, positive? Is work being done to the surroundings, negative, or to the system? So we're going to turn this into a bit of math to wrap stuff up. Okay. So calculate the work done when a gas expands from 500 milliliters to 700 milliliters. In the next lesson, this could be embedded within a chemical reaction. Okay? We're just stripping away we don't know what chemicals created this. Okay? But some reaction maybe made some hydrogen gas and went from 200 to 500 at 0.9 atmospheres. Okay? And then we got a second question we'll deal with on the moon later. Now I've got a conversion factor, how to convert PVs. We need liters and atmospheres for our PV, and a liter atmosphere is 101.3 joules. So that'll let us convert our units. So really a fairly simple relationship. Our work is minus PV. Our conversion factor has atmospheres in it. We already have atmospheres, so we don't have to do any chemistry 20 convert to torr, millimeters of mercury, or kilopascals. And we need our change in volume. I want it in liters. I'm not going to show all my work. Our change in volume would be the final 750 minus the initial 500, so a positive 250 milliliters. Okay, we got to keep track of the sign. So that's 0.250 liters. Okay. We only have one negative in this whole thing, so I want to put that down first. And we've got, obviously, our pressure is positive and our volume is positive. It's expanding, so the work is being done onto the surroundings, okay, which would be negative work from the system. Now, if we keep finishing this, our PV work will be in atmosphere liter units, and I'm going to throw in that conversion, or use our conversion. There's 101.3 joules for every liter atmosphere of PV work. So in joule units, to 2 sig figs. There's some ambiguity in my 500 milliliters in sig figs, but I'm kind of assuming that, or I'm saying this was measured to 3 digits, that's measured to 3, and that's only measured to 2, so 23 joules. Okay. One more question you're going to get used to. Internal energy is Q times W, and then we'll take some more steps, and in particular, get our volume changes from chemical reactions. You might have to count how many moles of gas is produced. Okay, and the one other thing, I'll kind of introduce it now, but it's really in the next lesson. Okay, you can get your work for minus P delta V, but in the next lesson, when we relate this to our reactions, we're going to go back to the ideal gas law. So PV equals nRT. Okay. Well, this P times delta V is work, okay, and PV is nRT. So you can also get the work from the nRT component. Okay. So work is minus P delta V, but it's also the change in moles times R times T. Okay. And we can get the change in moles from our stoichiometry in our chemical reaction. So I just put the negative in for the minus delta nRT. So last question of our first unit, really just keeping track of the in and the out. No real math here, no minus P delta V. So during a chemical reaction, a volume of gas increases, resulting in 350 some joules of work done on the surroundings. Some thermal energy is transferred to the surroundings, or asked what's the change in internal energy. So we've got all the numbers. Change in internal energy is Q plus W. We just need to figure out which ones are positive, which ones are negative, so we can do the correct sum. So I'm just going to rewrite out that visual. You may not need it. We've got our system. We've got our surroundings. Anytime energy is coming out of the system to the surroundings, it's negative. Positive if the surroundings sends thermal energy or does work to the system. So during a chemical reaction, I threw two different clues in this question. I probably wouldn't put two in a quiz. So the volume of gas is expanding. So that's all we really needed to know. Delta V is greater than 0. So the chemicals are doing the work on the surroundings. So that would be negative work. Okay. And then I kind of threw the wording in again. The work is done on the surroundings. So that's a bit redundant. Okay. So this work is negative. $425 joules of thermal energy, now I have to think of what sign to put in front, is transferred to the surroundings. So this is system to surroundings. This is exothermic. It's coming out. So that is also negative. Both of the work is done on the surroundings. So we just need to sum up those two negative numbers. You get minus 780 joules. So that's the change in internal energy of the system. Okay. So you might be like, oh, there's a change in energy. Doesn't that violate the first law of thermodynamics? No, the lack of a subscript here is just the system. The surroundings does the opposite, and the total change in energy is 0. Okay. So that's the heart of our lesson. I'll just flip back. I kind of went too quickly and negated to do the moon question on the previous slide. What if the gas expanded on the moon? Work is minus P delta V. Work is minus, well, the delta V is going to be the same volume, but what is the pressure on the moon? I didn't give it in the question. Is there an atmosphere on the moon? There isn't. There's no pressure on the moon. Okay. So same as in physics, if you apply a force with no distance, there's no work. Okay. Or if there's a distance with no force or no pressure, there's also no work. So if a volume of gas expands but there's no pressure, there's no work. So on the moon, there wouldn't be any PV work. Okay? There's no pressure. It's not pushing against anything. Okay? So we're going to practice that, particularly the work part. Okay? So this is Advantage 1, and we're in Chapter 4.